transfer function method for 2 degree of freedom systems. Also, the notes are being updated on Blackboard. So if your typed notes are out of date, I apologize, but you can download new ones on Blackboard. Okay, so before in 1 degree of freedom systems, we use the transfer function to solve for the temporal response of our 1 degree of freedom systems, and we can do the same thing here for our 2 degree of freedom systems, right? And again, the transfer function of a differential equation is defined as the ratio of a Laplace transform of the output of the system to the Laplace transform of the input of the system, right? So we had a 3-step process to run to solve these systems with our transfer function approach. Anyone remember the 3 steps? Remember 1? Yeah. Yeah. To take, perfect. Take Laplace transform. It's almost like we're learning something. Yeah, like it was just burned into my mind, right? Take Laplace transform, solve for x of s. You could have a 3-step program here to, I don't know. Okay, and then apply and then take the inverse Laplace. Let me write it then like this. The Laplace of f of s. No, that's not what I have. It's x of s, right? Little x, x of t. Correct? Solve for x of s and then take inverse Laplace transform. And that is x of t is equal to the Laplace of x of s negative 1. Pretty simple. Right. So I think the best way to look at this is just with an example. So this is example 5.5 in the notes. And so let's go ahead and solve for a x of t, a temporal response for a system. So let's do something a little bit more exciting than what we typically do. Let's do 2 masses that are coupled. So let's have mass 1. So let's define a kind of a nice flat line. Not sure quite how flat that looks, but let's have mass 1. And let's drop damping. Damping's hard for right now. And mass 2. Right, so we're going to have x of 2 and x of 1. And then let's subject this to an impulse, right? So we have 2 masses connected through a spring. And then let's just apply an impulse here. Let's draw it like this. I think that looks better. So what is the Greek symbol that we use for impulse? Delta. That makes sense. Delta E. And now let's scale that, right? Just F naught. So our F naught is going to scale it. All right. So now just think about this conceptually. Let's pretend you're playing polo. Right? That polo? The polo's on horses. Cricket? Cricket's? No. Cricket's like the bat. Croquet. Croquet. All right. So we're not very rich people sport here, I can tell. I watched a polo match once, and I was like, oh, dude, I got to get out of here. Like 3, 2, 1 financial crimes. with a different group of people. Anyway, so croquet, right? And you tap mass 1. How do you expect these two masses to move? Right? They're gonna. Which direction do you think they're gonna move? To that way, positive, right? Are they gonna come back? Are they just gonna go? What do you expect?
Well, M2 will come back to M1 after the initial compression, right? So they'll go that way and then kind of like.
Yeah, a little bit of it depends on the weight, but I expect they're going to move down and kind of oscillate in and out, right? So I expect they're going to move, they start like this, and then they maybe end up like this, and then they maybe end up like this, and then like that. Does that make sense? So generally, it's, or I guess this is time and this is distance. That's how I generally, but it could depend on the mass, right? If you tune these masses correctly, maybe one. No, I think even if you have a huge mass and a small mass, they're still going to move to the right. They're just going to move to the right slower. I don't think they'll ever be stationary. Force is mass times acceleration, and there's a force, and there's nothing counteracting it, so it kind of has to move in that direction. All right, but for the first initial setup, we need to build our equation of motion. If I tap x1, what's going to move more, x1 or x2?
X1.
X1, right? So we're going to assume x1 is greater than x2. That work? You can assume the other way. You'll get different equations, but you should get the same answer. Okay. So now if I draw my free body diagram, I'm going to just forget the orthogonal forces here, and we're just going to have k of x1 minus x2, and then we're going to have a back one and another mass, right? And then we're also going to have let's just draw it up here now, f naught of delta of t, I guess. That make sense? That's a pretty basic free body diagram. Probably should spend more time on it, but good enough for right now. So I get two equations, right? One equation for each mass. I'm going to get m1 x double dot plus k x1 minus x2 is equal to, and we have an input force on block 1, right? So that should probably be f naught delta of t. And then for block 2, I'm going to have m2 x double dot 2. There's an error in the notes. I spent so long on this, and this still errors. That's got to be right. Okay. Plus k of x2 minus x1 equals 0. Right? Taking the Laplace of both of these equations. So let's take so again, let's assume 0 initial conditions, right? That's going to make our Laplace easier. We like easy. So let's take the Laplace of the first equation. So we are going to end up take the Laplace of the first equation. We're going to have s squared m1 xs. And the Laplace of the second one is going to be x1 of s times k1, k2. So I don't have the intermediate steps. So this is what I have when I simplify these down. Okay, so I have m1 of s squared plus k is equal to x1 of s minus k x2 of s is equal to f naught, right? Because the Laplace of sigma is just 1. And then on the bottom, I'm going to have negative k x1 of s plus plus m2 of s squared plus k all multiplied by x2 of s. That seems right? Seems right to me. And again, in case you missed it here, notice how this one here is x1 minus x2, and this one here is x2 minus x1. And why is that? Why are those not the same? Yeah, the force is the opposite, right? You could have just had a minus. This is the same as negative x1 minus x2, right? Just bring the negative inside is all I did. Okay, and then again, why do we have capital X1 and capital X2 now? We didn't have that before. Because we have 2 degrees of freedom. So this, can we agree that this is step 1? Anybody disagree? No? All right, so what's step 2? Yeah, so how do we now? Because we don't have an x of s. We have x of 1 and x2.
Yeah, 2. So isolate those.
Yeah. Yeah, right? Pretty perfect. How hard could it be? So we want x1 of s equals some expression, and x2 of s equals some expression, right? Pretty easy. Take your 2 equations, make them both equal to x1, and then right? And then your x1s drop out, and then you have x2, then you do more rearranging. Same thing for when you want x1, you set them equal to x2. So I've done that to save us some time, and I don't think we need to walk over that. I have x1 of s is equal to f naught times m2 s squared plus k, and that's on top. And then on bottom is s squared m1 m2 s squared plus k m1 plus m2. Right? And then I have x2 of s, right? So s is our complex plane space, just in case we're lost on that. I've got f naught by k, which is s squared m1 m2 s squared plus k m1 plus m2. Okay, so now what do we do? Yeah, inverse Laplace. Same thing. Okay, so now we need to take the inverse Laplace. Are these expressions that we can see in our Laplace forming, our Laplace sheets? If I have one. The long answer to that is probably not. Right, so we need to break this up. You can break this up, break it up into terms we know. And how might we do that? How do you break fractions up? Partial fractions, that sound familiar? Maybe, maybe not. But we can use partial fractions. That's one way to do it. How else might we be able to do this? Maybe in MATLAB, right? Yeah. What?
It's like another one.
What's it called?
Symbol.
How do you spell it?
Type in just online actually. Yeah.
How do you spell it?
SYMBOL.
Really?
They do like.
It's online?
It's like Wolfram Alpha, but way better.
Really?
Yeah, it walks you through like step by step and gives you a reasonable answer. That's like advanced data rules.
Wolfram Alpha used to be free when I was in school.
Simple app. Yeah. They gotta like run CUDA method and Chelsea decomposition and all that fun stuff.
Fun. I will play around. Okay. Yeah, I would use, so what I did is I used a symbolic package in Python called SymPy, but you could do it in MATLAB too. Or you could do it with partial fractions if you are interested in that. So, okay, so Symbolab, something online, MATLAB has it built in, Python, SymPy, right? Okay, and then, cool. So any of these will work. If you could do it directly and just get your answers, or you can actually write them up and then take your inverse Laplaces on the sheet. So, right. So if we wanted to actually take the inverse Laplaces on the sheet with the terms that we have, you can get an expression that looks like this. Battery low. Well, that's odd because that's not what that says. Disagreeing with yourself. Okay. X of 1 of S is equal to F naught over M1 plus M2, 1 over S squared plus M2 over omega M1 times omega over S squared plus omega squared. Those look familiar? X2 of S is equal to F naught over M1 M1 plus M2 times 1 over S squared plus 1 over omega times omega over S squared plus omega 2. To get this, you had to use a little bit of trickery that omega 2 is equal to K 1 minus M1 plus 1 minus M2. All right, so if you looked at this long enough, you could probably do that with partial fractions. I think symbolic tool would be a much more efficient way to do it. So taking the inverse of these, we can get some terms. Right, so first, what's the inverse Laplace of f naught over m1 plus m2? Just, it's a constant, right? Nothing happens. So it just slides through. That makes sense? So I guess that this, oh no, wait, no. So the inverse of that is going to be, let me write it here. x1 of t is equal to f dot over m1 plus m2, right? And that's t plus m2 over omega m1 sine of omega t and then x2 of t is equal to f naught over m1 plus m2 t 1 over omega, t plus 1 over omega, sine of omega t. Right, and so if we look at this, these t terms are going to result in a system that does what? What? Yeah, just moves to the right kind of as a unit, right, more or less. And then these terms are going to result in a system that oscillates. And then this whole thing is just going to scale it out front. That makes sense? So if we have a system then, so in the notes I gave you some values, nothing super exciting. Right, so get a displacement that looks like that. That makes sense? That kind of what you expected to see as we move to the right? So the Laplace method, just like before, we can use this to solve for a variety of methods.